Oh, how about that? How about that? Okay, so, hey, here we go. Okay, so fundamental theorem of algebra. I already told you this. It's been a while ago, but I just couldn't resist. I had to let you know. Such a big deal. Fundamental theorem of algebra, remember, just says that if a polynomial has degree n, then you know it has exactly n complex roots, including multiplicities. The way the corollary is stated here is really much more useful than the way they state the theorem. The theorem actually just says if its degree is greater than 1, then it has to have greater than 1, or at least 1 0, where 0 could be a complex number. But that's not very useful. The corollary is much more useful because you can actually count the number. You can actually predict the number of zeros, complex zeros that a function will have, or that a polynomial will have. The other part of this that I told you, which I'll just jump up to real quick, is the complex conjugate root theorem. We talked about that. Remember we said that we talked about how complex solutions with imaginary parts always come in pairs, and those pairs are always complex conjugates, right? So I think I asked you this question before, like if we had a 5th degree polynomial, how many of the zeros could be real? How many could be real? 5 or 3 or 1, not 2 though. Because oh, that was hilarious. The complex solutions with imaginary parts always come in pairs, right? So you either have 0 or 2 or 4 of those, right? For example. And so there's the other part of that we already talked about. Okay, so what I'd like you to do then is just, first of all, predict. Oh, and when we talk about multiplicities, what's that mean? What's a multiplicity? Let's say we have something like, we have a polynomial in factored form that looks like this. Name a factor that has a multiplicity of greater than 1.
X minus 1.
Yeah, what's the multiplicity of x minus 1? 3. Yeah. Okay. So multiplicity just means to what power is a factor raised, right? So it might show up more than once. Do you remember, while we're on the subject here, do you remember what that implies about the graph of a function if it has a multiplicity greater than 1, about the x-intercepts?
It's going to be a tangent.
Okay, they're going to be tangent, right? They're going to be smeared out on the x-axis. Yes.
So as a graph would it kind of look like?
No, so it looked like this. So for example, I don't think the book goes into quite this much detail, but this is kind of cool. What could you tell me? What can you tell me about this x-intercept right here? Yeah, multiplicity of 1. What can you tell me now just think about this for a second. See if you can tell me something about the green and the purple.
The green is raised to an even power.
Ah, good.
The purple is raised to an odd power.
Yeah, good. So did we talk about that? Maybe we did talk about that.
Yeah, we did.
Okay. Yeah, so if you have a tangent x-intercept that bounces, right, that has locally even symmetry like this, right, where it's got just in the vicinity of the x-intercept, it's going to have symmetry about its own axis, then that's an even multiplicity. And if it's tangent to the curve but passes through, or tangent to the x-intercept but passes through the x-intercept, then it's going to be an odd multiplicity. Okay? So just some things that, it's kind of nice to know. All right, so how many zeros is this going to have, including multiplicities? 3, okay, find them. And I want all the complex zeros, including imaginary parts. Okay, so I take roll, you find those, please. Okay, so how are we going to, really nothing's changed here. You could have done this probably. I could have given you this problem a while ago, and you could have done it. we just didn't pop up in the book at that time. But what do we do if we're trying to find the zeros of a two-term, what's the way we've been using anyway, of dealing with a two-term polynomial? Okay, factoring it with pattern. What would the pattern be here?
A plus B times A squared minus AB.
So, sum of cubes, right? So we could write the first term as what cubed?
4x.
Second? 9. Okay, and then we'll just use the sum of cubes pattern, right? So that's going to split into, what is it, A plus B times, what's A squared going to be? 16x squared, good, and that's the quantity 4x squared, right? Minus, what?
36x.
AB, which is 36x plus 81. Okay, good. So, we're trying to find zeros, right?
Yeah.
So we're setting this equal to 0. And what do we know so far?
1 root 2.
Okay, so we get 1 right here, don't we? Right. Good. So we get x equals negative 9/4. Good. Now what about this guy? What did we say about this one before? About the big factor from any of the... Yeah, it's irreducible. It's an irreducible quadratic. So it's going to yield no real roots, but it has to yield how many complex roots? 2. And we know that they're going to be complex conjugates if they're not real, because they come in pairs, right? There's only room for one pair there. And the complex conjugates are going to come from, for us, are going to come from the quadratic formula, right? We'll just, what's our value of A? 16. B? 36, negative 36. C?
81.
So we end up with negative 36 squared. Oh boy, that's a big one. What do we got there? Let's just...
1296.
1296?
Minus 5,184.
Okay, minus square root of 5. What is it in here?
Isn't it supposed to be?
It's got to be negative. It's got to be negative.
I'm confused. How do we get that?
36 36 squared.
That's inside the radical.
What's that?
Are we doing?
Oh yeah, what am I doing there?
Oh, we're doing, okay.
Jeez. I don't know. What am I doing? So we get negative b, so that's positive 36 plus or minus.
One
Square root.
So say it again, 1296 minus
5184.
5184. There we go. So that is negative. Good. All divided by 2a, so 32. All right, so what is this? 1296 minus 5184.
Negative 3,888.
3,888?
That's what
Okay. So that's not going to probably reduce nicely, but that's all right. So 36 plus or minus the square root of 3888?
Yes.
Yeah, that doesn't look like a square. Negative. Yeah, you're right, negative. Okay, so then we got to reduce, well, let's let our calculators do this.
It's the 36 square root of 3.
I don't want to waste your time up here doing, you could, with or without a calculator, you could do that stuff. But let's go ahead and remind ourselves how we can do this easily with a calculator. That's my nice teacher way of saying I don't want to do that. So we'll go to apps. Which one are we going to use? Polysmalt 2. There you go. And we're gonna just solve this quadratic. So we'll go to polynomial root finder. We'll go order 2, right? And we could have just done the whole thing, really. But I'm not going to let you use your calculators on the test, so we'll just cheat on this part. So now we don't want real anymore. We're going to go over to a plus bi, because we want the complex roots, including the imaginary parts. And let's do that.
Do you want to offload?
I'm going to put it on auto so it'll give us a fraction if it can. Yeah, you want it on float. Float's fine. Okay, and so our first coefficient is 16. Second then we go minus 36x plus 81. And let's solve. And so it won't give us the fractions on here, unfortunately. But those are our two. Notice they've got i's in them, right?
Yes.
So those are complex, right? So we as predicted. We only got one real and two imaginary. Yes, sir.
Do you want it with the fractions?
Yeah, I want an exact one. So you would have had to. So how would you have done that? How would you have simplified 3888? I'll show you another trick on here.
Take out the square root of 36.
Square root of 36 goes into that?
Yeah.
Okay. Well, I'll show you how you can find that, though, because that's not easy to see, that the square root of 36 goes into that. Here's a good little trick. If you go to y equals, and you do, I got to remember how you do this here. You go, if I put in, I got to think how I do this here. Shoot. Oh, how the heck did I do that? There's a great little trick here, but I can't remember it. Oh, I know what it is. You put in the number, 3888. Here it is. So whatever the number is we're trying to, we know we've got everybody agree that we're going to get out of this, we've got a negative, right? So we're going to get an I out of this. Right? This number on top. We're trying to just simplify the square root of 3888, right? 3888I. So let's just take that part of it. Here's a good little trick for doing that. On your calculators, you can take the number that you're trying to, the radical that you're trying to reduce, the number that's inside the radical, and you're just going to divide that number by x squared. Okay? Then we're going to go to table. And you might, if you want to go to table set, you don't have to, but if you do, you can make it start at, yeah, that's fine. Just start at 0, and the delta should be 1, so you're going up by 1s. And then we go to table, and look what this does. Okay, so it tells us, I want you to just see, I'll make that bigger, how about? What does this mean? Now, y equals 3888 divided by x squared. And so for these values of x, these are the results. So for example, 3888 divided by 2 squared is 972, right? So what's that tell you then? This is really pretty cool. So that tells you that the square root of 3888, oops. Oh.
How did you get the table?
You just go second table. So this row right here, for example, then, is really just telling us that it's equal to 2 times the square root of 972. You see that? Because this number squared divides into the number that many times. Isn't that cool? So this number right here tells us, like this guy right here is telling us that it's equal to 9 times the square root of 48. So what do? I just go down the table as far as I can, right? So I get the last entry. So there's one. So I get 12. That's, we're going to go further though, aren't we? Because 27 has a 9 in it. 12 has a 4 in it.
There's 36 times the square root of 3. Yeah, that's right.
So yeah, there it is, right? And we know we're there. When we get to this one, this guy right here, we know we're there because what the number in the radical has no perfect square factors, right? 3 is prime. So that's the answer right there. Isn't that a cool little trick? So that's it. The answer is 36 times the square root of 3. Okay, so once again, how'd you do it? Here, you guys, I'm going to give you one. You have to do it real quick. Let's see, do I want you to reduce the square root or simplify the square root of how about square root of 3332. Simplify the square root of 3332. So did you get an answer?
Yep. Yes.
Okay. What'd you get?
14 times the square root of 17.
14 times the square root of 17 is right. Okay, once again, how would you do that? All you're going to do is take the number that's inside the radical, divide it by x squared and y1, and then just go to the table. All right, and I'm down too far. There it is right there. There's the last one. And I know I got it because 17, there's no perfect square factor of 17, right? So I know that's as low as I can go on the table. Okay? All right, it's a good little trick. What else? So how would you do this one then? Let's just talk about how you would do this. Find all the complex zeros, because you've been doing stuff like this. What would you do?
We could factor out a 2.
You could factor out a 2, yeah. And honestly, if I'm not told to factor this, right? I'm just told to find the zeros. So I wouldn't even have to factor out a 2. What could I do that's even better? Setting that equal to 0. Divide by 2. Yeah, so I could make this into x to the 4th plus 3x cubed plus 12x squared. Oops, sorry, 6x squared. Plus 12x plus 8. And then now what? Obviously there's no pattern that's going to work there. We don't have any strategy for a 5-term polynomial, but what could we do? Okay, synthetic division, and how am I getting the numbers that I'm testing, that I'm auditioning for zeros?
1, 2, 4, 8. Because 8 over.
Okay, good. So it'd be, right, they'd have to be, if it has rational roots, which it does, then they're going to have to be built, the numerator is going to have to be a factor of 8, positive or negative factor 8, and the denominator is going to be a positive or negative factor of a, which is 1. So really, I only have to try a handful here. Positive, negative 1, positive, negative 2, plus or minus 4, plus or minus 8. Start with the easy ones and just work your way down. And then once I get rid of one of those, once I find one hit, when I divide that in, this quartic is going to become a what? Cubic. And then hopefully when it's a cubic, I can maybe use factoring by grouping or something, right? If not, I could just keep going with more, just use that rational root theorem, right, and keep going. Okay? Does that make sense? And then eventually, on this problem, you're going to get to a point where you're going to get some irreducible quadratic, and then just do what you just did. Put it in the quadratic formula, get the zeros, right? Okay. What else? So last thing. How could we? So we know the complex conjugate root theorem. We know that complex roots with imaginary parts come in conjugate pairs. We also know, and this is pretty cool. This one I'm kind of glad the book does this one. If a polynomial has rational coefficients, and we end up with a root that has, that is irrational, it's real but irrational, then it has a square root in it, then guaranteed, that's also gonna be a part of a conjugate. Okay, so that's kind of cool. Now it only works if it has rational coefficients, and that's the only way it works. If it had like square root coefficients or something, then that wouldn't have to be the case. But if it has rational coefficients, then guaranteed, all irrational numbers with square roots in them have to come in conjugate pairs also. Okay, so what's that mean? This would be a pretty easy one here, right? What I'm asking you to do here is, I'll have you do a couple like this, where I want you to write the polynomial function of least degree that has integer coefficients, so integers are rational, right? The given zeros and a leading coefficient of 1. Well, this would be really simple. How would we build the simplest possible polynomial from those zeros?
X plus 3, x minus 3, x plus 6.
Exactly. This zero is going to correspond to the factor x minus negative 3, or x plus 3. That one corresponds to the factor x minus negative 6, x plus 6. And that one corresponds to x minus 3, and I just find the product of those, right? No big deal. Okay. What about something like that? What's going to be the least degree I could build? The simplest polynomial I could build with those zeros. It's going to be a fourth, right? Why not 3?
Because I always do that.
Yeah. Okay, good. Because we've got an I there, right? So that is a complex root with an imaginary part, and so it has to come in a complex conjugate pair. Well, let's think about that for a second. How would I write this root as a complex number in standard form? And it's been a while since we talked about that, but a complex number in standard form is just in the form a plus bi. So what's a in this case? 0, sure. So this would just be 0 minus 8i. So what would be the complex conjugate of that? 0 plus 8i. We don't write the zeros, of course. We would just turn that into an 8i, right? Yep.
Would A's sign also be flipped?
No. Conjugate only flips the operation between a and b. Yeah. Okay, so a stays the same. Does that make sense? No big deal. So all I would do then is I'm going to add that other 0, and I'm just going to make factors out of all those, right? So what's this going to work out to be? This is going to be the product of x minus negative 7, x plus 7, x minus 5, x minus negative 8i, so x plus 8i, x minus 8i, right? Now when I multiply these out, I want to be smart about it. Which for sure would I always multiply together? Yeah, I multiply the conjugates together, right? Because they're conjugates, and that uses the conjugate product pattern. What was the conjugate product pattern? Just in general, if we multiply a plus b times a minus b, what's the answer? A squared minus b squared, right? You know that's going to be the case. So what's this going to give us? What are these two going to give us then? X squared minus 8i squared, and 8i squared is negative 64, right? Because the I squared is a negative 1. You see? Oops. See how that works? Okay, so then we'll always multiply conjugates together because they're easy to multiply together, right? And then from there on out, we would just have to, just expand that whole thing, right? Okay, what about, did I not put one on there? I guess I did. Okay, what about one like this? What if I gave you one like this? What if I said 2, these are the zeros, 2, 1 minus the square root of 2, and square root of 2i. What's the least degree I could build if my polynomial has to have rational coefficients? No? Pi, how come?
Plus or minus square root of
Okay, good, because I have to have, this has to come in a pair, right? 1 minus the square root of 2 has to come in a conjugate pair because it has rational coefficients. And the complex one has to come in a conjugate pair no matter what. There's no way it can't, it always does. But if we're gonna have rational coefficients, that one does too, right? So that one's gonna get paired, this guy's gonna get paired with 1 plus the square root of 2, and that guy's gonna get paired with minus the square root of 2i, right? Yes?
If it were being brought to an odd group, would it not have to come to a pair?
2,
Say if it was the cube root of 2. would it have-
nah. It wouldn't, that wouldn't work, it wouldn't be you wouldn't end up getting rational coefficients in that case, so, no. It wouldn't work, so yeah, just with square roots. Yeah. One last one. Okay, this is, I'm gonna make this one simpler because I don't wanna take a lot of time on it, but what if we just had, let's cross out that one. Say we just had that part right there, that's it. What's the other missing root? Okay, -5 minus 2i. I just want to show you a little trick here. Because this actually, you kind of generalize this. Not that this is a huge deal, but it helps. So I'm just gonna find the product of all those factors, right? So let's take, so we're gonna end up with x minus 3 times x. Now what am I gonna do with this though? I'm gonna have to put this whole thing in parentheses, right? I'm gonna have x minus -5 plus 2i times x minus -5 minus 2i, right? Everybody agree? Because I'm always just subtracting the zeros from x to build the factors. Agreed? Okay, if you try to do it in that form, it's going to work, but it's going to be a little challenging. Do this instead. Look what happens if we take these two, this part of it right here. You can reorganize these a little bit. What if I distribute the negatives, and so I get x minus -5 is x plus 5, and then distribute the negative over there and get minus 2i. Same thing over here. I'm going to get x minus -5 is x plus 5 plus 2i. How could I reorganize those in a way that's going to make that product a lot easier? What can I do? Well, I mean, they're going to go away, but didn't we say earlier that it's always really simple to take the product of conjugates? Right? If I can write a product of conjugates, well, these are conjugates if I just group the x plus 5s, aren't they? See, then I've got hand minus 2i times hand plus 2i, right? And what's that equal to? This part right here is just equal to hand squared minus 2i squared, which would be plus 4. See what I'm saying? So that's kind of a good little trick. That makes it a lot easier. Because that's really not a very hard thing to do. I can expand that out using my binomial expansion, Pascal's triangle, right? That's coefficients are just 1, 2, 1, right? So what's that going to be?
X squared plus 10x plus 3.
Plus 4, right? And that wasn't so bad. See what I'm saying? So when you deal with complex, you've got complex zeros that have both a real and imaginary part. Just distribute the negative and regroup so they look like conjugates before you multiply. It makes it a lot easier. Okay, I'm done. You can work.